Right, so we're on our last 3 classes for us, and also 2 more classes for your actual calculus class. So we have class on Monday and Wednesday next week, but not Friday, because Friday is actually the beginning of finals week. So you want to check the final schedule and see if you actually have a final on that Friday, because some people have to turn right around and their first final is on that Friday. So double check. You guys, it's not your math final, so it's not that, but you might have a different class. So there's no actual classes meeting next Friday because it's the start of finals week. Last topics that we've got. We're sort of building up to being able to do curve sketching of some crazy curves. And so one of the topics that we're going to cover today is increasing or decreasing functions. And there's some vocabulary that sounds really scary, but it's not really all that bad. So a function is called monotonic. Mono means one. Monotonic means that it's going in one direction. So the function is monotonic if it's either always increasing or always decreasing. So monotonic could be it's always getting bigger. And an example of that would be y is equal to e to the x. That function is always getting bigger. It never gets lower. An example of a decreasing function, we could draw even just a linear function. If I drew you a line that has a negative slope, that's going to be a monotonic function, but it's always decreasing. Okay. In general, functions increase and also decrease in different areas. And so we have to be able to figure out when do we have functions increasing, when do we have functions decreasing. And so one of the tools that we can use is the first derivative to help us figure it out. So our first derivative test helps us determine the intervals on which we have increasing or decreasing, or that we have a critical point. And so we're not increasing or decreasing right there. So in terms of first derivative test working, it makes sense if you remember what the derivative really is. And if I ask you, like, what's the derivative right here on our graph? So maybe I put a point right here. And we want the derivative right at that point. What I'm actually asking you for is the slope of the tangent line at that point. And so if I drew you a point right there and I draw you a slope of a tangent line, this is a positive sloping line. But if I ask you for the derivative right here, I'm asking you for the slope of the tangent line at that point, and that's going to be a negative slope. And so the derivative, if the derivative is positive, then that's always going to happen when we're on places on the graph where we're increasing. So if I draw another point there and find the tangent line, that's also a positive slope. But if I'm coming on a side where I'm decreasing, they're going to have negative slopes. So what that means is that the function f of x is increasing specifically when f prime of x is greater than 0. When we have a positive derivative or greater than 0, then the function's increasing. Over on this side, I had negative slopes. Negative slopes are negative derivatives. So the function is decreasing when f prime of x is less than 0. Those are all negative. And then if we're actually at a critical number, and a critical number could be where your derivative is exactly equal to 0, or it could be where your derivative is undefined. If the derivative is undefined, we don't necessarily get something nice on the graph that explains what's happening. But if our derivative is equal to 0, we possibly have a maximum or a minimum value there. So at a critical number, if we have f prime of x is equal to 0 specifically, then we possibly have a maximum or a minimum value there when the f prime of x is equal to 0. If f prime of x is undefined, then we don't have a max or min there, but we might have something else happening. Something called an inflection point is often what will happen when it's undefined. So a max or a min, we would say that this right here, this point right here, would be a local minimum. Our derivative at that local minimum would equal 0. So right there, we have a local minimum. And up here, I have a local maximum. Derivative is 0. Do I have a global min or absolute min or an absolute maximum value for this function? Here's your hints. They keep going on and on forever, so no, I don't know what the global max or the absolute max, depending on which vocabulary word we're using there, because this keeps getting higher, so I can't say that I know what my absolute max is, and this one keeps getting lower. I don't know what my absolute min is. We don't have that, but we do have a local maximum and a local minimum, meaning that in the vicinity of where I'm looking at points, this is the highest point in this vicinity. And this is the lowest point in this vicinity of the graph.
So their f prime of x is equal to 0.
Correct. But those ones are f prime of x is equal to 0. Okay. Here's a familiar function. Y is equal to x squared. Okay. I put arrows on the ends. So this one does not have an absolute maximum. Does it have an absolute minimum? Yeah, it does have an absolute minimum. This graph is never going to go lower than 0.
And so we pretty much just have f of 0 equals 0.
So the absolute minimum is 0, and it happens at x is equal to 0. So when we give the minimum value, we're giving the y value that's the lowest y value. The lowest y value is 0, and it happens at x is equal to 0. Okay. In terms of where this function is decreasing, the function is decreasing anywhere that if I were to take a derivative, I'd get negative slopes. And so all the way from here down to 0,
Negative infinity to 0.
that's going to be a decreasing part. Oh, 0, sorry. That looks like the same color. Let's try red. Maybe we can see red better. So we're decreasing from negative infinity to 0. If I want to know where we're increasing is happening from 0 up to positive infinity. It would eventually go out to positive infinity. And right at 0, we have a horizontal tangent line. So right at 0, we have a derivative of 0. So right at that point, f prime of x is equal to 0. And that happens whenever we're increasing and then we switch to decreasing, or we're decreasing and we switch to increasing, we pass this time when our derivative is equal to 0. And so finding where the derivative is equal to 0 is we call them critical points, because those are places where we can be shifting from either decreasing to increasing or from increasing back to decreasing. So those are important points. If I didn't already know what that graph looked like, I could use the fact that the derivative is 0 at that point to help me guess where this would be a change in our derivatives. And so what we do is we create sign charts to help us figure that out when it's a graph I don't already know what it looks like. So let's talk about graphs we don't know what they look like already. So we're going to find the critical numbers of our function. We're going to determine the intervals on which the function is increasing and decreasing, and we're going to identify any extrema that we have. And I don't have a picture of this, so I can't use the picture to answer the question. I got to use the calculus to answer the question. Now, from a past life, when you were in pre-calculus, you may have remembered when you got to the polynomial section, some of them started low and ended high, or started high and ended low, and you use the degree of the polynomial and the sign on the leading coefficient to figure it out. So there's definitely tricks that you learned in pre-calculus that would let you sketch this graph. What we didn't know how to do in calculus, pre-calculus, but we didn't know how to do in pre-calculus was figure out exactly how high and exactly how low the things went, but we could give an overall shape for the thing. And normally what we did is we figured out where the x-intercepts were, and then we figured out if we were supposed to start high or start low. This one is a cubic, so it's an odd polynomial, and it's positive. And odd positive polynomials
And high.
So I would think of our cubic function, or was it that one? What do we think? Which one is x cubed?
The one.
Or is it this one?
The one going down is negative.
This one would be your negative one?
Yeah.
Yeah. Cool. So our cubic one would be this one here. And yeah, it started low and ends high. So ours would too. Ours would have a low starting point and a high ending point. But if I didn't know that, I can still answer this question. What I would need to do first is go find my critical numbers. So step one, I'm going to go find critical numbers.
One of them is 0.
Okay. To do that, I need to take the derivative. Okay. And this is never going to be undefined, so I don't need to worry about that, but I do need to set it equal to 0. I factored a 3 out. And I can factor this. I need two things that multiply to give me -3 that add up to -2. -3 and +1. And so then to find my critical numbers, I'm going to set x minus 3 equal to 0 and x plus 1 equal to 0. So I'm going to get x equals positive 3 and negative 1.
And also 0 because we have it after. Never mind.
Yeah, so if that was a 3x, you'd be right, but there's not a 3x there. So it's just these two numbers, 3 and negative 1.
I made a mistake.
That's okay. And so critical numbers are telling me where we've got horizontal asymptotes that are like this. So those could be the places where I change from being either decreasing to increasing or increasing to decreasing. So what we're going to do is set up a sign chart to help me figure out what's going on. So I'll make a number line and I'm going to put down the negative 1 and the positive 3. And so I'll circle them just so I can see them a little bit better. Those are my two critical numbers. And I'm going to choose test numbers on each side of those. So something smaller than negative 1, I could choose like negative 2. Something between negative 1 and positive 3. 0 is always a nice thing. And something bigger than 3, so I could choose 4. And so the question is, what am I plugging those numbers back into? Am I plugging them back into the original function, or am I plugging them into my derivative to figure out where these things are increasing and decreasing?
Oh, gee.
I want to know where are the slopes positive and where are the slopes negative. Yeah, we want to use the derivative. So good guess, but we want to use derivative. So back into my original function. So original function is going to give you the actual values. I want the slope. So I want the derivative, f prime. And we said f prime of x is 3x squared minus 6x minus 9. So I want to plug in negative 2. I don't even really care what the number comes out to be, but I do care that 12 plus 12 minus 9 should be something positive. Now you can put the actual number down. We don't need the actual number. I just need that in this region, we have positive slopes. And because we have positive slopes, that means that the function is going to be increasing in that region. Now I'm going to plug in 0. And so negative 9 will pop out. I really just care that it's negative in that region. So if my slopes are negative in that region, that means my function is decreasing. And then we're going to plug in 4, our last test number. And so 16 times 3 would be 48 minus 24 minus 9. That's going to be positive again. I don't care what the number is. I just care that positive numbers pop out. So that means that our function is increasing again in that region. So this question was asking, where is the function increasing and where is the function decreasing? So when I go to answer this, I'm going to set up 2 intervals for increasing My function is increasing from negative infinity all the way until I hit that -1. And so I'm going to put the u in the middle. My function is also increasing from 3 out to infinity. And then we also want to put where it's decreasing. We only have one interval where it's decreasing. And that's between the -1 and the +3. So we use the derivative in order to do the sign chart, because when the derivative is positive, that means the function's increasing. And when the derivative is negative, that means the function is decreasing.
Oh,
Is that okay? So question said, find the critical numbers. We did that. We got 3 and -1. Those are the critical numbers. Find the intervals on which it's increasing and decreasing. We did that. We found our intervals. And then the last thing it says, identify any extrema. So extreme values would happen at those critical numbers. Okay. So I went from increasing to decreasing right at -1. So if I went from increasing to decreasing, would I have a min or a max? There'd be a max up there, right? If we're going from increasing to decreasing, we got a max. And if we're going from decreasing to increasing, we'd have a min here. Okay. But when you go to actually give me those points, I need the x value and I need the y value. So when I want to give my extrema, okay.
Can you solve f of x with -1 and 3 for the y values?
So local max, we know the x value that we're going to use is -1. Do I want to plug that back into the original function or the derivative? OG. We want the original function because when we're doing a maximum or a minimum, we're talking about the function itself. So I want to plug this back into our original function, f of x, which was x cubed minus 3x squared minus 9x. We're going to plug the -1 into that. So we're going to calculate f of -1. So we have -1 minus 3 more plus 9. So -4 plus 9 would pop a 5 out for us. So we have a local max at 5. Let's see, I'll write that here. Local max of 5 at x equals -1. And then we want to find our local min. And so for the minimum, we're going to use the 3. So we're going to do f of 3. And so right here, I have 3 cubed minus, and if I actually multiply those out, I have another 3 cubed. So 3 cubed minus 3 cubed would be 0, minus 9 times 3. So I get -27 out. So we have a local min of -27 at x equals 3. You could see how I did that, but if we have 3 squared and we're multiplying it by another 3, that's going to be 3 cubed. So this is 3 cubed minus 3 cubed, that's 0. And then 9 times 3 is 27. We got to pop the negative on there since where the negative 27 came from. So that's from start to finish going through and finding the extrema, figuring out what our signs are going to be, and then that allows us to actually identify where our local max or mins are located. It's not super hard, but the process takes a few steps, and you have to be careful what you plug the numbers back into. So we should do another one. Make sure we know what we're doing. So we're gonna do exactly the same thing. We're gonna find the critical numbers. We're gonna figure out the intervals where it's increasing or decreasing, and we're gonna find any extrema for this function this time. So f of x equals 1/4 x to the 4th power plus x cubed plus 7. So first thing we want are critical numbers. We gotta take a derivative. So if 4 comes down and it gets multiplied by 1/4, that just cancels. So we have x to the 3rd power. And then plus 3x squared. And then the plus 7 will disappear on us.
Yeah.
I want to set this equal to 0. And I can factor out x squared from both terms. We're going to set x squared equal to 0. And we're going to set x plus 3 equal to 0. So if x squared is equal to 0, x is equal to 0 is one of our critical numbers. And x minus 3 would be another one of our critical numbers. We're going to put those two numbers on a sign chart.
-3. 1.
And with the sign chart, you're checking derivatives. So we're going to plug that back into our f prime. The numbers that are the critical numbers, I'll circle them so that I don't lose track of them. Those are my critical numbers. And then I need to choose numbers that are on each side of them to test. So I could choose -4. I could choose -1. I could choose +1. Now, my derivative might be easier for me to test written in the factored form like this. Doesn't have to be, you can use the original, but if this makes it easier for you to figure out the signs on things, you might want to do it this way. So if I do f prime of -4, and I plug -4 in here and I square it, I know that term's positive. And if I plug -4 in here and add 3 to it, I know that term's negative. So I know this one's positive and this one's negative, and you're multiplying those together. A positive times a negative would be a negative in that region. So I know that we're going to be decreasing that function. Then I'm going to plug in -1. So if I have -1 and I'm squaring it, and then -1 plus 3, then this term is going to be positive, and this term is going to also be positive. So we have a positive times a positive, so I know we get a positive in that middle region. And then finally, if I plug in 1, then I have positive times a positive again. So I get positive in this region. So what's interesting about that is that it didn't change directions. We're still increasing. What that means is that from here to here, around this critical number, -3, I was decreasing and then I was increasing. So this one would be a local min.
Local max is 0.
But I actually don't have a max or a min at 0 because I was increasing and then I was increasing again. So I didn't change direction. And so because of that, it's not a max or a min.
Unclear.
Likely what it would be after we do some additional calculus, we might find out that this is what we call an inflection point where it changes if the graph is kind of bowl-shaped up versus bowl-shaped down, but it's not going to tell us anything about the increasing. It stays increasing the whole time. So it's not a max or a min there. So in terms of us figuring out our, yes.
Do you do another derivative for that?
Yes, we do. That's called the second derivative test, or the concavity test, which we haven't talked about yet. Concavity test, it's just a scary word for saying, is something bowl-shaped up or is it bowl-shaped down? So when you go to do your curving of your graph, like, do you have it change from being something like this to something like this? Concavity changing, here it was bowl-shaped down, but here it's bowl-shaped up. So concavity might change at a particular point, but not actually be a max or a min. That will often happen where you have kind of like those sorts of things, where right here, this was bowl-shaped down, this is bowl-shaped up, but that's not a max or a min. That's just called an inflection point. So that takes a different derivative test, which we technically haven't learned yet. Unless you went over it today. Did you do concavity testing today? No. Okay. Didn't think so. So I need to say which intervals this thing is increasing or decreasing on. And so in terms of my intervals, I'm decreasing
From
all the way until I hit that -3. So negative infinity up to our -3 where we hit our local min. But then increasing, I don't have to use a U to break this into different intervals. It's just going to be one long increasing all the way from -3 up to infinity. So it doesn't change. So we went from -3, and when we got to 0, we kept going up. So I'm not going to stop. I'm just going to go ahead and go all the way to infinity with that. So in terms of extrema, I only have one that I'm going to give. So we have a local min, and we're going to use x equals -3. What we're going to plug it back into is the original function when I want to find my extrema. So my original function was the 1/4 x to the 4th plus x cubed plus 7. And so this is going to be 81/4. This one's going to be -20. Okay, so that's going to be negative, oh, not negative, sorry. 81/4 minus 7. And -7, or sorry, not -7, -20. Why did I say -7? minus 20, let's see, we can put 20 over 4 if we multiply that out. So 81 over 4 minus 80 over 4 pops out a 1/4. So that means that we have a local min of 1/4 at x is equal to -3. Is that okay? That's our first derivative test. First derivative test is used for our increasing and decreasing regions and to tell us about our extrema. After that, we need a second derivative to tell us more about the graph. So, second derivative what this can do is this can help us find concavity and inflection points.
F double prime x equals concavity slash inflection. I know that it has to equal 3x squared plus 6x.
So if I draw a graph like that, this is called concave up. And when things are concave up, the second derivative of the function is greater than 0. And if I draw a graph that's like this, that's concave down. And you could probably guess that the second derivative would have to be less than 0 for concave down. So we have like scenarios, sort of like the graph that we had talked about originally, where you might have something like this going on. And what we would say is that we've got a local max happening right here. And until we hit that local max, we're actually concave down on that graph. But when I turn around, I'm also concave down for this part of the graph as well. This is also concave down.
Concaves up once we hit the local min.
Well, what's weird about that is here's my local min. But look what's happening on this side. This side's actually concave up in here. So I was concave down for part of it, but then I switch and I end up being concave up over here. This is concave up. So there's a point that happens somewhere between where we're concave down here, but when we end up being concave up here, there's a point right in here where it switches, and that's called an inflection point. Figuring out exactly where that is requires calculus, but somewhere in here, we have an inflection point where we switch from being concave down to concave up. So we were concave down, but now we're concave up. So somewhere in there, we have a point where it switches, and where we switch from concave down to concave up or vice versa, we call that an inflection point. So in order to find all that stuff, we use what we call the second derivative test. So second derivative test says if x is equal to c is a critical number, and f double prime evaluated at c is greater than 0, then what that means is we have something that's concave up at that point, which would make this a local minimum. If instead the second derivative calculated at c is less than 0, then we're concave down, and that would make this a local max instead. And if when we calculate the second derivative at c, 0 pops out, it's not a max or a min. What it could be is an inflection point. So we want to think about what can happen it's possible for things to be inflection points. It's also possible for us to actually not have an inflection point there. So these are potential inflection points. And so when we go through a list of things, these are things that could happen, but we have to go back and still plug values in to actually figure out what is actually at some of those points. So using the same function that we were using on the last problem, I won't switch it over. We'll keep using our f of x was equal to 1/4 x to the 4th power plus x to the 3rd power plus 7. We took our first derivative and we got x cubed plus 3x squared when we did that. So now when we take our second derivative,
F double prime, I got f double prime x plus 3x squared plus 6x.
there we go. 3x squared plus 6x. Because when this is actually equal to 0, it's possible we could have inflection points. I want to go ahead and set my second derivative equal to 0 to find possible inflection points.
I'm gonna pull out an x from that. 3x.
So yeah, we can pull 3x out of that. Which means that if we set 3x equal to 0 or x plus 2 equal to 0, our possible inflection points are x is equal to 0 or x is equal to -2. Those are two things we're going to have to actually test to go figure out if they are inflection points. To test that, we do another sign chart.
-2 and 0.
So if we put -2 down and we put 0 down, what we're plugging these ones back into is the second derivative. So this is f double prime. And numbers that we can plug in, it's going to be the same as if we're doing it for the first derivative. So just something smaller than -2, something between these ones, and then maybe +1. But we're going to plug these back into our second derivative. So we said second derivative, probably going to be helpful if we write it in factored form. So we'll have the 3x and then the x plus 2 there. So we plug in -3. 3 times -3, and then -3 plus 2. This number, 3 times -3, is going to be negative, and then -3 plus 2 is also going to be negative. We have a negative times a negative, which means we have a positive for our second derivative. Positive second derivative by our concavity rules says that we're concave up in this region. And I plug in -1. So we have 3 times -1, and then -1 plus 2. That's going to give us something negative. 3 times -1 is negative, and then -1 plus 2 is positive. Negative times a positive is negative. So we're concave down in this region. And then we'll plug in 1. And so we have 3 times 1, and then 1 plus 2. Those are both going to be positive, so we have positive in that last region, which means we're concave up. So what we just showed is that these are both inflection points. They're inflection points because the definition of inflection point is you switch from concave up to concave down. So because at -2, we switched from concave up to concave down, this one's an inflection point. I'll put IP there. And at 0, we switched from concave down to concave up. So it's also an inflection point. So they're both inflection points. But we have to check, because if it turned out that we went from concave up to another concave up, then it would not be an inflection point. So we would just say it's not an inflection point. So we do have to test. So that means that we have inflection points. One of them is at -2 comma something, and the other one is at 0 comma something. To go figure out the something, I have to go back to the original function and plug in -2, and then go back to the original function and plug in 0 to figure out those parts. So this is f of -2. F of -2 would be 1/4 times -2 to the 4th power plus -2 to the 3rd power plus 7, which, if you trust me, pops out a 3. I'm just going to do that speedy like to get us out of here. So -2 comma 3. And then f of 0 will be 1/4 times 0 to the 4th power plus 0 to the 3rd power plus 7. So 7 is going to pop out of that one. So those are our two inflection points, -2 comma 3 and 0 comma 7. All right. Good work, guys. I know we're on the putting everything together parts of calculus for 21A, but you're doing good.